My name is Edi Palencia, and I'm going to talk about offline RL with RLlib today. So let me quickly tell you what is the agenda. So we're going to start telling you who we are and what offline is offering to us, and we're going to use that to actually make the case for RLlib and Ray and why we're using it and why it's good for offline RL. Also, we're going to try to show the benefits with a little bit of a demo. And at the end, we are going to talk a little bit about the challenges with offline RL, and also what is next for us with offline RL and also with Ray and RL. So let's get started. So we belong to a business unit in Microsoft called Autonomous Systems. We are Project Bonsai, and we are aiming to create a low-code or no-code AI development platform. The idea is to speed up the creation of AI-powered automation systems, and we also are trying to make it accessible to people that doesn't have any computer science background. So in other words, if you are an engineer, but you are not a data science or not a computer science, you should be okay to use our platform to create autonomous systems. So how we see this journey to create such a tool? Well, we start focus ourselves in the industry, and here you can see a picture of how we see automation in general in the industry. So you have what we call the connector level, where you basically are trying to aim to have data, right, about what is happening in your processes. And there is the next level where you are using that data to make some sort of predictions or at least understand what is happening. But the next level is about actually, using those predictions or those insights to make decisions or even create new business models or services. So just right there is where we are trying to work. And so we foresee, autonomous system either, starting with using the predictions to make maybe advices, to produce advice to some advanced users or to help to make informed decisions. But we can go as far as we think we can, in the user side, and try to actually put the systems to make the decision by itself. So our value proposition to achieve that is machine teaching. So machine teaching is a way to transfer knowledge from humans to underlying machine learning algorithms that combines, any AI technique that you can think of. And that is what we are trying to use. We combine things. And so to achieve to complete this value proposition, we have a complete solution to building, training, and deploying brains. That's the name of the product of using our platform. And those brains are high-level models that allows you to generate optimization or decisions. And those brains are conceptualized and very driven around the idea of deep reinforcement learning. It's not the only kind of techniques that we use, but deep reinforcement learning is definitely important for us. So basically, building a brain, we offer, machine teaching, tools, and that includes a domain-specific language, and also tools to actually move away from that language. But the language is a very low-code kind of domain-specific language to just to transfer your knowledge about the subject matter to the platform, and the platform will take care of all the machine teaching and all machine learning details and techniques. We also offer tools for simulation to accelerate the training and to integrate easily simulators and things related to that. And on top of that, we have of course, a engine for the artificial intelligence solution that is applying these machine teaching techniques. And last but not least, we offer a flexible way to actually deploy those brains that you are producing with our tools. So, as I said before, reinforcement learning is important and it's actually key for us, right? But reinforcement learning is hard, at least today. But we strongly believe that that is not going to be forever. We foresee a future where, reinforcement learning libraries are going to be there, kind of a commodity that everybody can use, reliable. And it's, again, we are still not there, but open source, I think open source is going to take us there. So open source over reinforcement learning for us is very important. That's why we are using RLlib. So RLlib is our bet to actually tackle the reinforcement learning using this idea that we have that open source can take you faster to this point where reinforcement learning libraries are there to be used. Yes, we think RLlib is good because it's comprehensive, it's extensible, and it's flexible. And it's actually because it's doing so good in the progress of becoming a established library for reinforcement learning, is that we think like extensibility is becoming more and more critical for RLlib. It's extensible right now, but I think to move RLlib to the next level, we need to invest more in extensibility. And based on, I'm gonna get back to the extensibility later because we actually took advantage of it. But the other important point that RLlib has is that, well, you need to deal with reinforcement learning. Very likely you need distributed training, and actually to achieving the machine teaching vision that we have, we strongly need distributed training. So that's why I want to put here the quick requirements for this kind of distributed training aspect, because distributed systems or platform for distributed systems, there are good ones out there, well established, but the particular things that we have to keep in mind is that for reinforcement learning and specifically for us, is very important simulation. And simulation brings a lot of small pieces to this distributed aspect. And this thing is very dynamic. Reinforcement learning is very dynamic. Everything is changing all the time because it's actually what reinforcement learning is about. It's about decisions, and decisions are affecting what is happening. So that introduces a lot of dynamism, not only in what you want to learn, but also in the platform where you are actually learning. So, and last but not least, the execution paradigm that you're actually going to need for this kind of technologies is cannot be a lazy compute kind of paradigm. It has to be more just in time. When you actually need to compute something, you want that thing get scheduled right away. So that is what just in time means. In opposition to our more kind of lazy execution, which are good for very data driven kind of machine learning, where you have a lot of data and it's a good idea to actually figure out like a schedule of what you need and when you need it and try to optimize to that. That is good for other machine learning scenarios, but for these kind of scenarios, it's not the best. So that's why we use Ray. So it's not only because RLlib, it's actually because this distributed training aspect, and this complexity actually requires a framework a little bit more aligned with those requirements. And we think that Ray is exactly doing that. It's filling those specific holes that we actually can find in other distributed computing frameworks, right? So more concretely, we have a microservice architecture, so we need something that can fit right in without imposing too many things. So we were able to actually use Ray only for training, which is what we want, without affecting anything else, which is good. So so Ray plays very well in that regard, and also because we are Kubernetes based, so it was very important for us that Ray were able to play good with with Kubernetes, and that is the case right now. We saw a tremendous progress in that regard since last year, so that is great. Yeah, and the AI focus, I think Ray has a lot of AI focus, underneath, which is extremely good. So that's why we are using Ray. So, but going back to the purpose of this talk, so we have a challenge, and the challenge here is simulators. So simulators are hard to implement. Sometimes, if you are working with an industrial case, they are going to be slow, very slow sometimes. And even worse, sometimes there are no simulators at all, or it's not about that it's hard to create those simulators. It's about, those simulators are maybe not possible. So maybe it's not our case, but imagine, that you want to go to something like healthcare or things like that. It's just not possible, right? So, but people have data. So that is pervasive, right? So people have data and may sometimes only have data. So that's why we start looking at offline RL. So we need it. So offline RL, like from a very simplistic point of view, if can solve the problem that our user will like or will want to just train a brain, train these decision-making components directly from data, right? Without any simulators involved. So this is the comparison of a very, high level overview of the user journey. So today you have to design a simulator. You have to create and package that thing using our SDK and to put it inside our platform, and you start training. But you need the simulator, right? And that takes a lot of time. Sometimes take most of the time of a project. But what we want to offer is the possibility, if you have data, or you can collect the data, just bring the data, upload the data to our platform, train the brain. So because of that is what motivates us or move us to start looking at offline RL. So what is offline RL, right? Is just about simulators and no simulator? Well, it's not. It's more than that. It's even more than training from data. So to get the idea of that, let's try to compare offline RL with machine learning techniques. Let's start from the very beginning. I don't want to go super technical on reinforcement learning because I'm assuming you are gonna get those details from other talks. But roughly speaking, so just trying to compare offline RL with reinforcement learning as it is with a simulator. So you typically have, here at the left, we can see, the classical on policy or the more prototypical version of online reinforcement learning, which is, you use your policy, or in this case, the policy is our brain, to roll out, to make decisions, and you take those decisions, a batch of them, and try to improve your policy or brain in this case, right? And that is the classical one where you are all the learning process is a step by step following. This collect some data, improve, collect, improve, right? So you have the other option, which is off policy, where you are constantly in a decoupled way, collecting, experiences, collecting the data, right? So the policy and the brain, is receiving, the state or, the observation of the world and making decisions back and but that is happening independently of the learning process, right? And for that, you have the typical replay buffer, and that is the classical of policy, right? Those two are, about the agent directly acting over the world. So you need a model of the world, which is your simulator, right? As opposed to that, you in offline RL is actually just about somebody, just using what we are going to call a behavioral policy or multiple of them, right? Just record a bunch of experience. When and how those experiences were collected, ideally, we would like to, say, well, we don't care, right? We would like to take advantage of any experience, right? So that is what offline RL is about. You just record them, those experiences, and you try to learn from it. And you get the best policy that you can from that, and you deploy. So that is the ideal workflow. And a simple way to also figure out this, you can think of, online is like trying to play basketball, going to the court and playing against somebody, right? Offline is trying to sit in front of YouTube and see videos of Stephen Curry, Michael Jordan, LeBron James, people that are good at it, or maybe other guys that are not good at it, but a kid that is able to jump very high, or a kid that have a good move, a good way to handle the ball. So, it's just about watching recordings of somebody acting, right? So that is a simple way to compare offline versus offline. So now that we compare, actually, from the operational point of view, let's try to compare from, what actually are the benefits of offline RL. So because we compare the operational aspect of reinforcement learning, classical and offline. Now let's try to compare offline with machine learning, because people can think, okay, but this is data. Is this like supervised learning? Where it's not. So the main difference is that, as you saw before, so in all of the cases, offline or not, it's about making decisions. It's about the agent, learning, that under some condition, which is the state of what he's observing of the world, making a decision. That decision can affect the next state that he's going to observe, right? So it's active. So this agent is making decisions actively over the world, which is going to yield into behavior. This is totally different to machine learning, because in machine learning, it's just about recognizing something. So even if that recognition looks like a decision, that decision is not affecting, in principle, should not affect what this algorithm is going to see next, right? So this is the very important difference. So in machine learning is totally passive, and it's about recognizing something, perceiving something. And actually, reinforcement learning can have that inside, right? You will need, the agent can make sometimes, or most of the time, it's going to need to have some sort of perception idea inside to actually be able to make decisions. So with that in mind, how are we, leveraging RLlib, right? And, in this talk, we want to show you very quickly how can you use RLlib for that. So basically, it was actually quite, I would say, given the complexity, was quite simple. We implement a new algorithm, we reuse existing RLlib components to do that, right? And actually, last but not least, we actually extend a little bit RLlib in the CLI to make the process even faster, the development process even faster. So very quickly, I'm gonna talk about the algorithm that we select. So we select an algorithm called CQL. We select that because it was simple. It's by simple, I don't want to mean that is, the idea is simplistic. Actually, the idea is pretty good. We consider that it's a strong idea. But the implementation, the moment that you put that to work, it was not that hard. That's what we meant by simple. We observe good performance of that of this approach. It's able to actually improve Sometimes it's able to improve over the behavioral policies. Imagine that you are watching a video of a kid that is not a super good player, but there are good moves that he's showing in the video, and maybe you saw another video of another kid that have other moves that are different, and you are able to learn from all of them, and you become a better player. Well, SQL is kind of able to achieve that, which is super good. And that is about combining suboptimal, decisions in some episodes. So that is strong. So we don't see that. We didn't see that in other algorithms, and also other algorithms were not able to work in complex, scenarios. So very roughly speaking, here is the math about CQL. So CQL is conservative Q learning, and roughly speaking, what CQL is trying to do is trying to approach a policy that is lower. It's a lower bound. It's like the best lower bound that you can get from the data that you are seeing. That is actually lower bound in the true policy, the true policy that you would like to have, right? So this is good because it's safe, in the sense that and it's dealing with a big problem with learning from recording, which is you get over optimistic. Imagine that you start looking at Michael Jordan, you're going to think like you can do exactly what he's able to do. Well, that is you don't want that kind of behavior, and that is a typical mistake that you're going to see in some algorithms, like going over optimistic. So this thing is actually by design saying, okay, no, I want to lower bound my behavior by lower bound the Q value. So that is what the question is doing. But it's also kind of a good lower bound because it's actually trying to maximize the value of decisions that are actually supported in the dataset. So basically you want to push up values, related to actions that have support in the data set, push down those actions that you don't have evidence in the data sets for those kind of decisions. So that is roughly speaking what SQL is doing. Checking on time. So SQL, so we were able to implement SQL by reusing, stuff that we already have. So because the way that SQL works, it's actually, you can extend another existing algorithm and use SQL over it. So we were able to slightly modify SAC and DQN algorithms that are in RLlib a little bit to make it, suitable for extensions. So, and with that, we create losses that are over SQL losses over SAC and DQN. And we, with that, we get two new agents, SQL SAC and SQL DQN. So, which is great. So this talks about extensibility, what's possible. I think it could be even easier, but it was a good experience, speaking to, creating this. So last but not least, we create this tool. It's a tool for, when you are testing or dealing with this thing, you would like to be able to test, to perform experiments with different levels of optimality. Imagine that, you want to simulate a kid that is not able to play very well, or somebody that plays relatively well, or you want to simulate somebody that is an expert. So you want to generate those data sets and test your algorithms or your environments, or just take an algorithm that exists with an environment exists and test that the tool is actually doing what it's supposed to do. So we create this tool to automatically generate multiple data sets, by default generating 5, with different levels of optimality, using just a YAML, the YAML syntax that RLlib was already offering for rollouts and for training. So basically, RLlib dataset command is just built on top RLlib train and RLlib rollout commands to use both of them together to actually, run, create those data sets for you to test. So this tool was very handy. And so at this point, let me show you with a demo how the benefit that our users are getting from offline, and I'm going to compare in the demo with online. So Yep, let me switch to the demo. You are looking at a training for online. So we're training a brain using 23 simulators at this iteration speed, and here you can visualize actually one of those simulators, like performing the task, which is trying to balance the ball in the center of the plate. Here you have the offline one, right? Here the scale is different because we are not trying to evaluate using simulators. Simulators are not used at all. We are just trying to we use the estimation of values to try to track the progress. For both, you can visualize the distribution either of the accumulated return or these values. But the interesting part, the benefit for the user is here. So in the teaching part for online, you typically say the source of the data is a simulator located in this package. For offline, you just have to say the source is actually data, not a simulator, data located in this data set with these coordinates. That's it. Everything else is underneath. So the magic of offline RL is not being, affecting the user experience. For the Internet of Time, I already deployed several brains here. So we have several opposite different cases. The first one that I'm going to show you is a brain trained with offline with bad data, suboptimal actions. As you can see, the brain is not able to balance the ball. So you see the effect of bad data. So now let me show you the opposite, training online up to convergence. So using simulators. Perfect performance, is able to balance the ball very quickly. That one took 100,000 samples to get up to the point of convergence. So now let me show you a brain trained offline with 10 times less data. As we can see, same performance, 10 times less data. Now that we saw the value of offline reinforcement learning and compare that with online classical reinforcement learning in our tool. So let me quickly tell you what is challenging with offline RL if you want to try that. So you are gonna see this in any paper or blog. Is distribution of shifts is the first challenge. And there, CQL, if you use CQL, well, you are safe in one part of the problem. But the other part of the problem, which is, unseen states, that part, well, is about your data, right? So you have to be careful with that. And that it also combines with the fact that, well, you are in offline RL, so there is no exploration. So you have to account for that. So your data set is important. And last but not least, because these two things combined is the fact that you don't have a model of the work. The next challenge is evaluation. So how you evaluate the fact, with a metric that the policy that you have is good or not. So there are methods for that, and this problem is known as of policy evaluation. And in our case, we recommend FQE or model-based, depends on, how fast how much time do you have in your budget to actually perform evaluations. But those are the two methods. And last but not least, what is next? So for us in our journey, so the next thing to try with Ray is placement groups. We haven't played with that, but we are seeing it's a great tool. So we are going to start taking advantage of it. For RLlib, we are aiming to start doing model-based things inside RLlib and contribute that back, of course. And last but not least, in offline RL, our next step is about combining online and offline together to actually deal with the exploration challenge. So that's it. If you have any question, please let me know.